So, we briefly talked about length scale of mixing in terms of scalar microscale for mixing, how it plays a role in determining the scalar distribution rate. In the last few days, we talked about spectrum of turbulent magnetic field. In this lecture, we will go into the length scales of mixing, spectrum of scalar fluctuation, all those aspects. Okay. So, you remember we talked about an autocorrelation function in the last lecture, but that was from the Lagrangian point of view. It was in terms of the time separation. So here, I can define a function like this, where essentially the separation not in time, but in space. And most of the time, that's what is used. So here one can have a normalized scalar correlation function in this manner. So basically it's a normalized spatial correlation function. 0 means there is no separation. So this is essentially the variance. This is the normalized scalar correlation function. Essentially what you are seeing in the denominator is nothing but scalar variance. Okay? As we discussed earlier, when the spatial separation is equal to 0, this function takes a value of u. Here, as you can see, if you put r equal to 0, numerator and denominator are the same. So, if there is no separation, the signals, scalar fluctuation signals, are perfectly correlated with each other. If the r magnitude goes to infinity, this will go to 0. There will be no correlation. For homogeneous isotropic turbulence, now isotropic means everything is identical in all three directions. So it really does not depend on the direction anymore, it depends only on the magnitude. Homogeneous means it is independent of x. Wherever I actually evaluate, I'll get the same value. Okay. So in that case, effectively, one can get a scalar integral length scale using this relation. Just integrating the normalized scalar correlation function in this manner. If you go back to previous day's notes, you will see a similar thing existed for defining the integral length scale for turbulence. At that time, the correlation function was defined based on the velocity fluctuation components. The concept remains exactly the same. Clear? And you might remember I told if you draw a parabola with the same slope at r equal to 0, where it cuts the r axis, that gives you the measure of the scalar microscale. In a similar manner, the second derivative of f with respect to r at r equal to 0 gives you the measure of scalar microscale of scalar. And under homogeneous isotropic turbulence, you can show that it takes this kind of form, and from there, effectively, you can define the scalar dissipation rate of a scalar in terms of this is the variance, this is the scalar microscale, 6 is the number. Please note in the case of velocity, the this number was 15, and here this one is essentially the diffusivity, the scalar in question. Clear? For fully developed turbulent flow, one generally gets L phi. That means integral length scale of scalar approaches to this, which is the longitudinal length scale of turbulence. Taylor microscale depends on the Schmidt number, which is a material property given by this kinematic viscosity to molecular diffusivity is your Schmidt number. If you are thinking in terms of scalar as temperature, then it is going to be the kinematic viscosity. This one will be thermal diffusivity. It will become Prandtl number. Clear? So, essentially, the Taylor microscale for scalar is related to the Taylor microscale of turbulence in this manner. Roughly speaking, I think probably one should actually put a scaling sign, because here you have got 6, and in the case of the turbulence, the number is 50. Okay? So, the scalar spectrum is linked to this correlation function R phi using the Fourier transformation in this manner, where this is the wave number vector. Once again, wave number we discussed in the context of turbulent kinetic energy spectrum. It is inversely proportional to the length scales of turbulent eddies. Yeah? The reverse action, inverse Fourier transformation, will give you the correlation function in terms of the spectrum function. Okay? And the above equation, this equation, can essentially be used in order to actually get the scalar variance in this manner. If you put R equal to 0, if you go back to the definition, if you put R equal to 0, this becomes the variance. As you can see, this was R0G is essentially the variance. So that's why if you put R equal to 0, you get this. You can see if you put R equal to 0, this is going to be e to the power 0, which becomes 1, right? By the way, I think if you have done Fourier transformation before, you know that I essentially is the imaginary number. That's what I'm talking about. So from this equation, one ends up with this. For scalar energy spectrum, that means how this quantity, the scalar variance, is distributed over different wavelengths. In other words, how the scalar variance contribution for different eddies are distributed can be actually expressed in this form. Okay. This delta means not Kroneker's delta anymore, it's a delta function. For isotropic, so all the concepts that I actually talked about can be actually extended to scalar velocity correlation like this, or covariance of scalars. That means this is one scalar, this is another scalar. If you have multiple scalars in your system, you can generate covariance of them as well. Okay? In other words, it's a cross correlation between them. If I have an isotropic scalar fluctuation, I can write this, one can derive this one. The derivations are long. If you are interested, look at chapter 6 of Pope's book on turbulence for the derivations in the context of turbulent kinetic energy spectrum. These ones you are not going to get in Pope's book, but the same concepts are borrowed. Scalar variance therefore will be obtained by this. Clear? As I told, it's more or less borrowing the same concepts. In the case of turbulent kinetic energy spectrum, if I integrated the spectrum with respect to wave number, I got turbulent kinetic energy. Turbulent kinetic energy was what? Half of the average of Ui prime. This one is basically playing the role, scalar variance is playing the role of the kinetic energy in the context of scalar variance. Clear? The conceptually it is clear? From here, as well as for homogeneous isotropic turbulence, takes quite a bit of intermediate derivation, but if you do that, ultimately you will end up with this expression for integral length scale or scale. Same thing exists for longitudinal length scale of turbulence under homogeneous isotropic turbulence. Effectively, here it is going to become the turbulent kinetic energy spectrum. Here it will be U prime. Basically, it is going to be the kinetic energy part. Ui, U1 prime, U1 prime. Right? Similarly, scalar dissipation rate is given by this. If you remember and go back to your notes, you will see the spectrum for dissipation rate of kinetic energy was kinematic viscosity here, kappa squared times the E kappa. Same thing appears here. Here, the only difference is here it is the mass diffusivity or the diffusivity of the scalar, and here it is the scalar spectrum rather than turbulent kinetic energy spectrum. Concepts are identical, only they mean different things here. So that's basically the spectrum of scalar dissipation rate. Scalar time scale is defined like this. Again, similar to, if you consider, this one has no unit, right? Scalar doesn't have any unit. What's the unit of this? Scalar dissipation rate? 1/second, right? So 1 divided by 1/second gives you second. So it's basically this one gives you measure of the time. If we consider this to be constant, then one gets this relation, but obviously it is subject to this assumption, may not be valid. But we can see that how the scalar variance under homogeneous isotropic turbulence essentially drops like this. Because if you consider homogeneous isotropic turbulence without any chemical reaction, there is no generation mechanism for scalar fluctuations. The only mechanism is the dissipation rate, and as a result, it's exponential. Clear? Now, the resolution is not great. I don't know whether you can see. At the back, can you see? Whether you can see from there. So it starts like this. According to Kolmogorov's hypothesis, Kolmogorov's theory, in the inertial range, the turbulent kinetic energy spectrum had in log scale had a slope of -5. So it starts with that. Okay. If we consider that L phi, integral length scale of scalar, is same as integral length scale of turbulence, and if we consider Schmidt number is equal to 1, that means the diffusivity is same as the kinematic viscosity, then what you are seeing here, that bit is essentially the turbulent kinetic energy spectrum as well. They are identical. Okay? Now things start to change if I change mid number from unit. This side is gaseous fluid where mid number is less than 1. You know, whatever I am talking about Schmidt number, that is valid for Prandtl number as well. So even if you consider your scalar to be temperature, it depends on Prandtl number. If you consider air, Schmidt number is 0.7. So talking about this side. Hydrogen, much smaller than 1. Okay? So you can see the roll off of the spectrum. In the case of turbulent kinetic energy spectrum, which is the case of Schmidt number equal to 1, starts around Bhowmik length scale. And then, because of viscous action, drops. Right? Think about the definition of Schmidt number. It's kinematic viscosity divided by the diffusivity. So if Schmidt number is less than 1, whether diffusivity effects are becoming stronger, isn't it? Clear? As a result, this roll off for the scalar spectrum starts to happen at relatively larger length scale. Okay? Where the diffusivity of that means molecular diffusion process does not play any role is called inertial convective range. That means scalar distribution is determined by inertial process and the advection induced by inertial processes. Okay? Molecular diffusion does not play a very important role. How the scalar fluctuation is distributed from the large scale into the small scale. Okay. Happy with that? But from this point on, wherever the roll off takes place, this is essentially scalar dissipation rate killing the fluctuations and basically giving a fully micrometric state. And this range is called inertial diffusive range. Why inertial diffusive range? Diffusive part probably you can understand. But look at the kinetic energy spectrum. It is still within the inertial range. Viscous action still doesn't play a very important role. That's why inertial diffusive range. Clear? Now, if Schmidt number is much greater than 1, in that case, as Schmidt number increases, what happens to the diffusive action? It becomes stronger or weaker? Weaker, right? So effectively, the rolling off takes place at much higher wave number, in other words, much smaller length scale. But for kinetic energy, it has already happened here. The length scale at which this roll off takes place is lambda b, which is called Bachelor length scale. Now, this clearly you can appreciate that where this spectral roll-off takes place, this is very strongly dependent on Schmidt number. If you think in terms of the heat transfer, once again, replace Schmidt number by Prandtl number. So, effectively, case kappa C1, where effectively the rolling off takes place, is given by this, where this one is kappa eta is inversely proportional to the Bhowmik length scale. FC D for 4 if you actually write it down in terms of 2 pi divided by another length scale, that length scale which corresponds to this bad number is called Bhowmik of Porcine length scale. Just information sake, nothing else. This one, for Schmidt number greater than 1, it is given by this, and kappa b is the wave number corresponding to Bachelor length scale. I have already talked about this. So this is how it looks like. Okay? Couple of things to note. If you are thinking about a direct numerical simulation, effectively in direct numerical simulation, the smallest length scales need to be resolved. So if you are dealing with gaseous flows, where Schmidt number is less than 1, resolving the smallest length scale of turbulence, Kolmogorov length scale is good enough. Matter ends there, right? Because spectral rolling off takes place here. So if you are thinking about heat transfer DNS or mass transfer DNS for gaseous flows, it's fine. There is no extra bar because you have to anyway resolve the Kolmogorov length scale. If I'm talking about liquids, and especially high molecular weight liquids, heavier the liquids are, Schmidt number increases. For DNS of high molecular weight liquids, I have to resolve up to this wave number. That means I have to resolve the length scales which is much smaller than the Kolmogorov length scale. And that really presents a huge burden. This one, when I normalize it to integral scales, it is the compensated one. I go in terms of the Kolmogorov scale. There is a type I'll correct and send it to you. So again, you can see the spectral roll-off takes place in a different way. So now the idea of parameterizing. In the inertial convective subrange is given by this. You can still see kappa to the power minus I sitting there. There is a different constant, however, though. Previously, in the case of turbulent kinetic energy spectrum, you just had epsilon raised to the power 2/3. Yeah. Now you have scalar dissipation rate sitting there, and epsilon has the dissipation rate of kinetic energy raised to the power minus 1/3. Okay. You can actually come up with the idea of velocity spectrum, make both of them epsilon, you will get epsilon raised to the power 2/3. For high turbulent Reynolds number, both kinetic energy and scalar spectra are energy containing processes, so inertial and inertial convective subrange. As a result, time scale, integral time scale of scalar mixing scales with L11 over U prime, which is any turned over time. Effectively. They are of the same order. Obviously, the values are different. The theoretical value for this is called Bhowmik of Porcine constant. Is 2/3. 2 times 2/3 gives you 4/3. That means 1.33, and this one is 1.5. So you can understand this is the order of unity, right? inertial diffusive range. That means, once again, inertial diffusive range is valid for Schmidt number less than 1. So, fluid flow is still turbulent within the inertial range, but now the diffusion roll-off has started. Given by this, see that exponent has changed significantly. That's why you are seeing this rapid decay. Until now it was minus 5/3. Now it has become, in this region, it has become minus 17/3. That's why much rapidly it is coming down. In the viscous diffusive subrange, this is valid for Schmidt number much greater than 1. Now, turbulence is going through a decaying process because of the viscous action, but diffusion roll-off has not started. Bachelor essentially came up with this functional form. There are alternative functional form by equation. And combining all of those behaviors, but clearly see whether it is Bachelor's parameterization or Creation's parameterization, there are a couple of things you need to consider. One is, previously it was a kappa to the power minus 5/3, now it is kappa to the power minus 1. Okay, there's a change in slope. Other thing I want you to actually note, kinematic viscosity explicitly appears in this picture. So if somebody tells the turbulent process effectively gives rise to things which is only flow properties, that's not necessarily the case. Essentially, when it comes to turbulent mixing, the molecular property still continues to play an important role. And you can perhaps appreciate from the fact that depending upon the Schmidt number, which is a molecular property of the fluid, the scalar spectrum behavior is going to be very different. Clear? So if I consider all of those conditions, this is a model spectrum, an approximation, which follows all the necessary limiting behaviors. Here, this is the FD is essentially this function. FB is given in this manner, and this CD is not really a constant. You can see, depending upon Schmidt number, it can change, but for large Schmidt number, it goes to lower approach. It is also dependent on Taylor scale best Reynolds number, but mostly it is dependent significantly on Schmidt number. Once again, you can see the signature of molecular properties are coming in. Relation between the integral length scale of mixing to turbulent large scale times length scale as a function of Schmidt number. Okay? You can see that when ln of Schmidt number is 0, ln when is 0? Log of 1. So when Schmidt number is of the order of unity, these quantities tend to be 1. But when you are considering this side of the plot, that means Schmidt number greater than unity or smaller than unity? Smaller than unity. Then they can be quite different, as you can see. Clear? And a value also depends on Taylor microscale Reynolds number. When Schmidt number is greater than unity, it converges to a value close to. Physically, I can have different size of blobs to begin with. If I allow them to develop under turbulence, eventually the integral length scale, irrespective of what I started with, will become of the order of turbulent length scale. Think about that you have a diesel engine cylinder, you have injection of fuel, let's say it has evaporated. Depending upon the injection characteristics and its evaporative properties, you'll have different size blobs to begin with. That integral length scale might be different to begin with, but we are talking about gaseous flows. If we allow it to mix for a couple of eddy turnover times, it will come back to around this range. Okay? The scalar dissipation constant CD can also be evaluated in this manner. These are the things which we already talked about, so I'm not essentially reiterating that. You have already seen. These are the different length scales. Obviously, we talked about Kolmogorov length scale several times by now, so I'm not spending any time in telling what the physical significance of that. This is the Obuchov-Porsen length scale. Similar, the only thing is instead of kinematic viscosity, I'm changing to diffusivity. This is what the spectral roll-off occurs for Schmidt number less than 1. Okay? This is the Bachelor length scale. Even with this. So, and as I told, this is where the roll-off occurs when Schmidt number greater than 1. Based on this functional form, you can clearly see Bachelor length scale, where spectral roll-off occurs for Schmidt number greater than 1 is smaller than the Kolmogorov length scale. That means corresponding wave number will be higher. Clear? As I told, during direct numerical simulations become extremely troublesome for high Schmidt number fluids of that case. You can do the fluid flow part, no problem, but if you are interested in mixing, then you will run into trouble. Okay? So, I'll talk about some ways to actually circumvent the problem. What is done? First, as I said, in the context of heat transfer, replace Schmidt number by Prandtl number. The reason I'm talking about Prandtl number now, because people have tried to actually circumvent this thing from the context of heat transfer problems, because in industrial applications, heat transfer in liquids is often encountered. So, these are some ways to actually be expressing the non-dimensional mesh size. Delta X is the mesh, L is a characteristic length scale. So it has to be smaller than, basically it is trying to tell, in order to actually have DNS, your delta X has to be smaller than the Kolmogorov length scale. And basically that is shown in this manner as a function of Prandtl number, Nusselt number, mean Nusselt number, and this is for natural convection, as a function of Rayleigh number. Okay? And this is valid only when Prandtl number is less than 1, that means I'm talking about gaseous flows. When Prandtl number is greater than 1, then I will do this. Okay? As long as my delta x essentially is smaller than this, so I am not going to consider in terms of the bachelor length scale. If I know what Rayleigh number I am going to simulate, what Prandtl number I am considering, and if I have some estimation of Nusselt number beforehand, if I know some experimental values of Nusselt number, or if I already know some Nusselt number correlations which is available in the literature and estimate the Nusselt number, I can put everything there, right? And based on that, I can actually come up with the value for the delta x. There are alternative expressions in this manner as well. So you can clearly see, this is only for natural convection, by the way, because people looked at high Prandtl number natural convection in DNS context, and that's where these were actually proposed. This is a very, very dynamic field. People are doing many things, so in future there might be some other things in the case of force convection as well. Effectively, I'll also change this one in the updated slide. H is essentially height of an enclosure, so I'll change it to L characteristics. This is basically based on a characteristic lens, nothing else. So they essentially included global measures of thermal transport such as Nusselt number, and they showed that time average, temperature profile, volume average, dissipation rates are insensitive to the under resolution of bachelor times length scale mostly. So even if I don't actually resolve the bachelor length scale, if I can actually get some idea about Nusselt number a priori, dictated by that, I can choose my grid size and still carry out a simulation which will give us sufficiently accurate values. Okay. So we talked about the key length scales of turbulent mixing, similarities and dissimilarities of the spectrum of scalar as well as